Thank you very much. The content remains the same. Okay, first of all, good morning everybody, and thank you very much, very really an honor for putting together this wonderful ICAM conference. And now I want to thank also my collaborators, Isao Inoue, who is supposed to be here. He's going to be coming, he needs to talk tomorrow, and also Ine Takagi, both from Japan, and then the other set of collaborators living in the antipodes, that is in Argentina, Maria Jose Sanchez and Rozenberg, two theorists, and also Pablo Levi and Carlos Sacha from University of Buenos Aires, MEA, who are experimentalists and responsible for some of the experiments that I'm going to show you later on. Okay, so here you have a set of references of the different work that we've done in our efforts to model the effect of resistive switching. Okay, so we've seen resistive switching systems yesterday, just to remind you, because this is the first talk. The typical ARAM system has two metallic electrodes in a capacitor-like structure with a dielectric, which is a transition metal oxide. For transition metal oxide, the big surprise is that almost anything works. So you can go from very simple binary structures like nickel oxide, copper oxide, or titanium oxide that we saw quite a bit yesterday, and increase the complexity down to multi-component perovskite systems like procedure lanthanum calcium manganese oxide, which is these famous manganite systems. Also, you can use the cuprates. So a very wide variety of systems can be used. This comes clearly as a big surprise. So, since these systems are important because they may be used for next generation of memories, the typical experiments that one sees have to do with switching. This is the resistive switching, that's the name of the effect, and also hysteresis because it's a memory. So when you do switching experiments, you apply a certain voltage protocol as a function of time, and each time you apply a pulse of voltage, you get a pulse of current. But the interesting thing is that after each one of the pulses, you can leave the system in a metastable state, which remains for a long time. That is the non-volatile memory, which can have a low current or a high current. So this corresponds to two different resistance states, which are stable. The counterpart is hysteresis experiments, in that you run the voltage up and down, or the current up and down, and what you see is that the system switches from a low resistance state to a high resistance state once you go through certain thresholds in voltage or in current. So, in front of this phenomenology, a theorist has to account for an effect which is quite general and appears in a wide variety of different systems. So, clearly one has to extract some very generic features, and the model cannot be very specific, because otherwise it will not be general. So what are the universal features of transition metal oxides? And I think the most important are that this system naturally builds spatial inhomogeneity. It can be driven by the way you fabricate them, but even if you try to make samples which are very well controlled, there is always some degree of phase separation that occurs even at the electronic level. That's why these systems have a wide variety of ground states that can be tuned with temperature, composition. They are very subtle systems. So you can tune them through metal-insulated transitions, and that's why we found that the most studied systems in the past 20 or 30 years are the cuprates and the manganites, which are the hallmark of the transition metal oxides. On top of that, these thin films, which also open the door for the rejuvenation of this film. The thin films are fabricated using techniques like pulse laser deposition, which sometimes generate systems which are not completely homogeneous, such as single crystals, and also RF sputtering also works. So in general, all different techniques that may have quite a number of effects work. So an example of even a system which can be made clean has electronic phase separation has been very much highlighted in the case of the manganites, where these AFM pictures show that the system has a natural phase separation between insulated regions, which are the dark regions there, and more conductive regions, which are the white regions in the middle. So you see that inhomogeneity plays quite an important role, and that is one of the things that we want to keep in order to try to come up with a model. So the first model that we introduced in collaboration with Isao Inoue and Maria Jose Sanchez several years ago was just out of intuition because very, very little was known at that time. So the model we proposed was called the domain model, in which we imagined that in between the electrons there was a big insulating matrix which remained inert, and then you have domains near each one of the two electrons, and then a large domain that acts like a buffer that separates the two interfaces in the middle. In this system, we put some carriers that could tunnel from the electrons into these domains and then hop between these domains and cross the system and produce different theoretical effects. This model was studied by numerical simulations, like the master equations, and give rise to some interesting results. The first one is that when you apply a protocol of voltage pulses, positive and negative pulses as a function of time, this is a result of a simulation, you see that the current has spikes also that coincides with the voltage pulse application. But when you look in detail what happens there, you see that after each one of the spikes, up and down, you see that the system commutes between two well-defined values of the current. If you invert the current, you have resistance, and then you see the two values of resistance that the system can be switched in, and which is reminiscent of the experiments that I showed a moment before. So these results do not look that impressive, but the less trivial things that gave us some confidence until this model was capturing something non-trivial is that when you put many pulses that can be erased or right, you see that the behavior is quite different. If you apply the erased pulses, the system is saturated at the maximum current and does not go beyond. Therefore, when you invert that, you have the resistance being at the lowest level. And then when you apply a set of right pulses, you get a systematic suppression of the current. And when you plot this in a semi-log state, you see that that produces multi-level values of the resistance that increase in this linear fashion, and that was very reminiscent of early results from the group of Alex in Houston. So these non-trivial results told us that we were probably in the right track, and that this very simple model was already capturing something. One of the predictions of the model was that important effects occur at the interfaces, and that thing is something that has been eventually validated in more recent experiments. Another prediction of the model is what we call complementarity, and namely that what happens in one interface is pretty much the opposite of what happens in the other interface for symmetric samples. So in this model, where every time you apply a voltage pulse, you have injection of carriers on one side, and you have leakage of carriers on the other. So the different occupations of these two sets of domains commuted up and down in a pretty out-of-phase fashion. So that predicted that what should happen at the two pulse contacts should be opposite, and if you do a planar structure with multi-contacts, you have access to the measurement of what is the resistance value of the contacts. So since we are saying that everything is occurring at the interfaces, it is sufficient to measure the resistance contacts. So in experiments, you can measure these values, and you see that on the two extremes of the sample, the voltage is commuted in an opposite fashion. That is the validation of this complementarity prediction of the model. So these were the two predictions of this very simple model. However, the model also had an important drawback. And the important drawback is that when you look at the hysteresis, the IV curves do not look like resistive switching. This is more like a diode switching, that you have one diode and then the inverse diode. In any case, this is not the pinch resistant hysteresis that Professor Chua has emphasized yesterday. So you can play around with all the parameters of this model. We have done that until you get completely bored, and there is no way you make this system to switch. You can make it asymmetric if you bring in asymmetry into the model parameters, but they never cross. So there's something fundamental that was missing in the model, and that is what we're going to discuss later on. So that model was introduced in 2004. In in the following years, much more is known about the systematics of the resistive switching. In particular, we now know that there are systems which have what is called the non-polar and the bipolar resistive switching, which has a very well-defined differences in their phenomenology. So for the non-polar, we know that only, at least as far as I know, only binary systems show non-polar, and there are some modeling that has been proposed. Yesterday we heard a little bit about the random circuit breaker, and also we did our contribution introducing the idea of remote transition at the level of these domains that I described before. In any case, what I will focus today is on the bipolar switching, where I'm going to just incorporate to the early ideas the new features that have become quite clear in recent experiments. One is the idea of in the current being inhomogeneous that was emphasized by the group of the IBM. Also, the existence of oxygen vacancy ionic diffusion that was emphasized by many groups, in particular the group of Buster and Regina Dittman and Alex Ignatieff. And yesterday we heard also about the group in Hewlett-Packard with Stan Williams and his collaborators. Another aspect that we're going to incorporate is the effect of the Schottky interfaces. The only thing that we will retain is not the details of the band bending itself, but only the fact that a Schottky interface produces a high resistance at the level of the contacts, and that will turn to be a key feature. And finally, we retain also the complementarity that I was mentioning a moment ago. So this is going to be the focus of what I'm going to talk right now. Okay, so we go back to what is this dielectric and what goes on in this system when you produce a resistive switching. So many of these systems need to be formed. When electroforming, we just think that this promotes the existence of these oxygen vacancies and or defects, and that these things get organized in some fashion through the effect of electroforming. Eventually, you're going to get a lot of these defects and vacancies organized in conductive paths. So I'm not going to say much about what is the nature of this conductive path. This is just to say that the conduction seems to be inhomogeneous, so there may be many inhomogeneous channels. These can be separated at different distances, so depending on the particularities of the size of your sample, you may see things that scale with the area or not. I'm not going to get into that. I'm going to just retain the existence of these preferential paths. And from this path, we're going to retain the fact that there are regions near the two electrodes which are important and have to be modeled more specifically. So the idea will be just have this conductive path going through the sample, and we're going to model one of those. So the model is like this. It's very simple. It's just a linear one-dimensional path in which we're going to split it in different beams or domains that go through the system. So this thing is characterized by three regions, one bulk region, and then two interfacial regions where the resistance is much, much higher. We know that the resistance in the interfaces are the ones that control really the two terminal resistivity of this system. So in each one of these beams, we assume that there is a certain concentration of oxygen vacancies. So oxygen vacancies can move from beam to beam under the action of the applied electric field. So there is some diffusion given by this exponential of minus d0, which is an attempt rate for this oxygen migration. But also when you apply a voltage, there are voltage drops in each one of these domains. So that will enhance the probability of jumping, of moving oxygen vacancies from beam to beam. On top of that, the probability will also be proportional to the concentration of oxygen vacancies that may jump from A to B, and also will be proportional to the amount of free phase space or the amount of empty sites that we have in the other beam. So this is the simple probability that rules how oxygen vacancies migrate through this one-dimensional chain. Now another important point is that each domain is defined by solely the concentration of oxygen vacancies. Now, given a certain concentration of oxygen vacancies, delta I times some model parameter, you get the local resistivity. So the resistivity at each domain only depends on the density of oxygen vacancies. Now the parameter A characterizes whether you are in the bulk or in the interfaces. So say in the bulk, for simplicity, we just consider A to be 1, and then at the interfaces, since they are Schottky interfaces and the resistance there is enhanced, mostly not because the system is different, structurally it's the same system, but the band bending produced by the proximity with the metallic electrode produces the change in the band structure, and that thing depletes carriers or whatever. In any case, you have a large resistivity there. So each vacancy that you put on the interfaces will produce a relatively much higher contribution to the two terminal resistivity. So here we have other parameters, AL and AR, which for simplicity we're going to take for a moment to be equal, and which are much larger than 1. So then you just have in the model a simple one-dimensional resistive network where each one of these resistors depend on the oxygen concentration. So you're going to have a landscape of resistance. You apply a voltage pulse. In each step of your simulation, carriers will change in this oxygen vacancy will hop from domain to domain, and you recompute all the voltage drops in each one of these things. So you have the fields, and with the fields you recompute how the vacancies matter. So it's a very simple model. You can think of this as being really stripped down to the bones, really bring to light which is essential and what is not. So the total resistance of the system will just be the sum of the resistivity of all these links. Okay, the first surprise is that if you start with the model with homogeneous resistance, which is natural for a system which is an as-is preparation, you just take it from the oven, and all the concentration of vacancies should be homogeneous. So you start with the density of vacancies, which is homogeneous. This is the shade of gray. And after doing the forming, what you find is that the density of vacancies changes dramatically. They get depleted from each one of the two interfaces, and they accumulate in the inner side of the bulk region. So here you have the density relative to the initial one. So we start with an homogeneous value of 1, and what you see after the forming steps, that you get depletion of the two interfaces and accumulation up there. So the forming is just having the system being run up and down for several loops, and this is what you get after the first few loops. In order to get more detail into that, this is what happens with the forming. You start with the resistance of the system, which is homogeneous, and then after you ramp it for 5 loops, so this is the first loop, you get a change of the resistance. Second loop, you get that. Third loop, you get that. So the system, in the language of Professor Chua, it started at an initial state and got attracted in its basin of attraction to some dynamical state with a critical cycle, which becomes now repetitive. So what we focus is what happens during this cycle where a system has already been formed and where the density of vacancy profile went from the trivial homogeneous one to this non-trivial one. And that happens because you get a periodic driving of the system. You change the driving, you may get a different type of but this is the driving that you get for the usual hysteresis loops. Okay, so before showing you the results, I want just to set up a little bit of the thing. If you have a typical IV resistive switching characteristic, you get that when you plot R versus D for this hysteresis loop. What you get is the switching from high to low and vice versa. So this is what you expect for a simple hysteresis. Now, when you go to symmetric samples, what happens instead of having this, what we get is this odd-looking resistance versus current or resistance versus voltage loops, which looks like the table with legs. The table with legs is not a nomenclature that I invented. It's something that was introduced by the group of Alex Ignacier in a paper in 2005. And these are the results that motivate my curiosity in his paper. They were rather poor, but essentially correct, and certainly mysterious. So this is the resistance versus voltage that you get along different application of a pulse protocol, and when you do that in a systematic manner to get the hysteresis loop response, you get exactly that this system has this table with legs in which the loop becomes very non-trivial. So it goes up, down, recuperates there, goes down, and up again. And this is independent of the system. This is PLCMO, and this is YTCO, two famous transition metal oxides. These are the colossal magnetic resistance, and this is the Cooper. Okay, so we have the model, so we can investigate in detail and understand why this thing happens there, and when we do the model results and see what happens in this after the system has been formed. So this is after loop 5, 6, and 7. You see that the table with X is beautifully recovered. So we have a model, so we can ask all types of questions and understand why this thing happens as it happens. So going back to the density of the profile of vacancies that you get after the forming, we see that we have depletion on the two sides. Now this looks a little bit different because it is in a semi-log scale to emphasize what happens with the vacancies that go into the interfaces, because that there is where all the action happens. So this is the accumulation that you get in the interior part of the bulb, but then here is where all the action happens. So we start, let me now drive you through the half of the cycle of hysteresis. So we start at 0 voltage at the black dot. The black dot corresponds to this profile of density where you see a pile-up of vacancies on the left. So this thing comes, the pile-up on the left comes because before that you had the negative voltage part. So the negative voltage part is the one that produced this accumulation. Now you go into the positive part, and in the positive part you start pushing these vacancies out from the extreme left region, and the reason is because since we have most vacancies there, the resistance is going to be much larger there. Remember that the resistance is connected to the vacancies through this parameter A, which is much larger here and here than in the middle. So these vacancies here have a big effect, so you have a large resistance up there, and the resistance is nothing but the local electric field, because since this is a one-dimensional system, it's serial, so the current is the same for all the beams, so the voltage drop is directly proportional to the resistivity. Therefore, the electric field there is just the resistivity is a measure of the local electric field. So the local electric field there is large. Therefore, that's why you push the charges from this extreme into the system. So you get in the second step there red, all the charges, all the oxygen vacancies being pushed across this interface, and eventually they will get pushed into the bulb. The moment they go into the bulb, they don't contribute more to the resistance, to the total resistance, because the parameter A in the bulb is 0. So the interfaces are Schottky barriers, but the bulb is completely regular. So the effect of these vacancies basically vanish the moment they go into the bulb. That's where you have the green spot there, where you don't have any more accumulation of vacancies either on the left or on the right. So this corresponds to the low resistance state right there, where these two, where the densities are minimal. Now, the moment you no longer have a strong accumulation on this side, and you have the vacancies split in the two sides, the voltage drop becomes strongly enhanced there. Why? Because before you have all the voltage drop in here, but now the voltage drop goes half and half. Therefore, you can start moving vacancies on this side. So the vacancies that are in this proximity of the interface start migrating in, and that is the reason why you go from the low resistance state there into the high resistance state there by pushing vacancies that were in the bulb side, in the rightmost part of the bulb region into the right interface. And eventually increasing the voltage more, you get a pile up on the other side, where you start decreasing the voltage, but still with the same polarity, the pile up remains there. Therefore, you go back to the mirror image of the initial state, where you go back from blue to this spot there. So that, I just took you around this whole cycle, and you can understand perfectly what is the reason for this apparently odd, non-trivial resistive thing. As an additional test to this, we said, how about if we relieve the condition of symmetry? So this we can easily investigate in the model by just changing the ratio of the coefficients AL and AR that describe the Schottky resistance in the two interfaces. So instead of having a ratio equal to 1, we just decrease one of the two and get a set of data from the symmetric system to a very asymmetric system where we decrease the resistance of one of the two interfaces. And what we see is that this thing goes from this symmetric looking state to something that looks more reminiscent to the simple high-low switching. And in the experiments, you can introduce asymmetry by many different means. The most simple one is just to have a big electrode and a small electrode contact, but you can also change the type of the material. But in this system, just to try to get everything under control, we took a different route, and the only thing that we've done is just on one of the two interfaces, we just pulse it systematically with the same polarity in order to bring to the positive electrode a lot of oxygens, therefore curing, having very few defects over there. If you have few defects, the resistance goes down. So by just systematic same polarity pulsing of one interface, you introduce asymmetry to the model, and you see in the experiment that you can get impedance CMOS and YDCO, both resistive loops that look very similar to the one that you can get here, and you can get a similarity that goes down to the very little detail, like this round part there and here, that is reminiscent of what is in here, and this drop over there, and all these features can be understood very easily. How? Well, just noticing that the resistance here is the sum of two interfaces. So in one interface, the only thing that happens is that you get in and out vacancies. As you put vacancies into there, the resistance goes down. If you take the vacancies out, the resistance goes up. If you increase the number of vacancies, the resistance goes up. If you decrease the number of vacancies, the resistance goes down. So you get in one, say the left interface, a very simple high-low switching. Now, because of the complementarity, the same thing happens on the other interface. So now we have that one is doing this, the other interface is doing that. For instance, when this is high, the other is low, and when this is low, the other is in high. Right? And each one just commutes at the edges. Now when you add the two to get the two contact resistive value, which is usually what people measure when you have fields, but this thing has been done in bulk systems, planar systems with multi-electrodes, so you have access to each one of the two interfaces. What you see is that if you add the two to get the total resistance, you get this table with less reminiscent of external. When you have an asymmetric system, you have on one side the same thing, but on the other side, since you increase the resistance, you have a similar loop but smaller, and when you add these two, what you get is precisely that odd shape that I showed you a moment ago. So you can understand this to the very detail from this real-world model. So in order to finish, I'm going to show you some work in progress, which is another non-trivial test for this model, which is the mini-loops. So mini-loops is also a typical thing that you can do on systems with memory. So we start with the usual loop in one of the two interfaces, so we have this high-low computation of the resistance as a function of the voltage. And what we do is, after doing several loops, we stop there, and then we decrease the amount of voltage exposure. And when you do that, you get a smaller loop. If you then stop there, you get a smaller loop, and when you stop there, you get even a smaller loop. So this is also, in other words, the multi-level resistive switching that you can produce in these samples, but now in all the gory detail. When you go to the model and do excursions of different voltage amplitudes, we'll see that you start from this big loop, major loop, and then you can stop there and get all these smaller loops. And you can see that the validation is quite to small details. Like, for instance, the threshold here is the one that is changing. Similarly there, the threshold is changing, but the computation threshold for the switching from high to low is pretty much independent of the voltage. So to a large degree of detail, the model is predicting things that you can go and measure. So this provides, I think, full validation for the model. So in order to sum up, I just introduced a very simple model, I would say stripped to the bones of what is essential in this resistive switching of bipolar systems, and I show you that there is good agreement with non-trivial experiments. So this indicates that indeed the key features are well suspected by everybody, but in this time we are putting this into a very well-defined mathematical framework, which just shows that with this model you can get what you see in the experiment. This is the existence of spatial inhomogeneities, the role of oxygen vacancies, and predictions of the model is the non-obvious oxygen vacancy profile that you can see in the system. I show you where the accumulation goes after the forming, what is the goal of forming, and so on. So other things that this model shows is that symmetric systems, perfectly symmetric systems, are bad because typically you get in this table with length a high resistance state. Only the low resistance state happens at very fine tuning of the system. So if you try to produce a very beautiful symmetric sample, you're going to have a hard time finding resistance switching at all. It is there, but it's hard to find. It's much better to have an asymmetric system. So already this model is providing good guidance for system design. Also, we can explore and have started to explore the effect of degradation. If you remember the results that I showed, all these table with legs is a function of loops. You see that there was some drifting of the system. The drifting of it is nothing but the degradation of the system, and it's that the vacancies get trapped into the bulk, and then it's harder to get them out of the bulk again to the interfaces. So those are features that you can also start to understand. And finally, a challenging point for future investigation is try to put this model in contact with realistic parameter calculation that can come from ab initio determination of the model parameter. So that is the goal for the future, and that will really boost our capacity to predict these resistance switching systems. Thank you very much for your attention.
Well, thank you very much for joining us control. So we have plenty of time for questions.
You pinch hysteresis loop that you showed, you trace that with a sinusoidal signal, and so what frequency is that?
The pinch hysteresis only occurs in the non-pinch
That's a
one.
measurement, right? So is that a measurement? Experimental curve.
You
show the pinch hysteresis.
Yes. These are pinches. These are pinch hysteresis measured in the experiment in one interface.
And also the resistance. Anyway,
This is resistance. This is resistance is a function of voltage. So if you plot IV, this will. So IV will give you pinch because you have crossing.
Right. And this is experimental.
This is experiment. This is theory.
Okay. And what signal are you using? Input signal is a sine wave.
Okay, that's an important point. This is measured in the same sort of way that was emphasized yesterday by Stan Williams. What you do is you apply a pulse, and then you measure with bias voltage what are the resistance states. And then you apply another pulse, and you measure. So you apply pulse, measure. So it's not a continuous measurement. So it goes step by step.
So you reconstruct the final.
That's right. That's right. So each one of these points is an experimental point that corresponds to the.
So what's the practical problem in trying to measure it with the actual signal? What's the problem?
Well, one of the things is that these systems are planar systems, so the contacts are well separated. So then you have to apply a strong pulsing in order to push the system from state to state. So that is one thing. And if you go to thin films, then you cannot have access to what happens in each one of the interfaces. Now, in the Memristors things, which are very, very thin, I think they are pretty much one build shot interface by construction. And that's where they can do these things.
If you studied them, I missed the answer. What was your evidence for giving so much importance to the interface layers? That is, it appeared to me that 80% of what you presented is that once you make the last couple cells in your one-dimensional chain very resistive, then a lot of cool things happen. I mean that what was the importance for it? And just to give an alternative, people who study one-dimensional chains often learn the importance of weak links, but it is not obvious that where the weak links should be. You could have those high resistance links somewhere in the middle, possibly leading to analogous design.
That's right. Okay, so what we learned from the first model was that the interfaces were important. Because why do you need this three-layer structure, like the two interfaces and the buffer in the middle? Well, it turns out that if you use 2 or 1, which would be like we did that as the initial step, you don't get a switching that you can make that you can put in contact with any experiment. So the first thing that came clearly from there is that the 3 things. That already had some good comparison with the experiment, so it told us we are in the right track. But at that point, it was not clear at all that the interface was playing an important role. That is something that we preserve for the second model. And that is also because, well, some people emphasize the existence of chunky interfaces, that resistive interfaces needed to be there. But one thing that comes out from the model is that having strong resistivity in the interfaces is crucial. If you don't have that, then you don't have resistivity. So at least one of the two interfaces has to be very resistive.
So I understand your model only works if you have this resistive interface, but is there empiric evidence that this is really happening?
If there's empiric evidence that the interfaces are resistive, I think so. There is a beautiful experiment by the group of Alex and Initial where they have a tip going through the system, so with resolution, with very good resolution, you can scan the system and see where the resistive switching occurs. And in that experiment already it shows that all the resistive changes occur at the interface. So at least in that system. Now, yesterday we changed all the Hewlett-Packard data. In that system, I think it is an interface made, artificially made. In the sense that you have a metallic system, which is the one with a lot of oxygen vacancies, and then a more resistive thing. And then you just push the system around in that interface. So it will be one of these interfaces. It will be like two interfaces, and each one is at the nanoscale. But you don't need to have a nano system. You can have just a piece of bulk material that you just push from the drawer, and hand paints, and the contacts will be the nano regions where all the action happens.
If you would consider your electronic system and the ionic system separately, right? Because I think what everybody believes is the transport mechanism, the change in the resistance is an electronic effect, so you modulate your charge carrier concentration or whatever, but the memory effect is based on the distribution of ions. Then you come up with very different boundary conditions, for the ionic system. So for example, for the ions, we assume, well, the electrodes are kind of blocking, right? But the ions are blocking, block at the electrodes. So if you now move ions will pile up at that interface. On the other hand, if you look at, like, for example, Schottky contact, what would happen is electrons would not pile up, but there would be.
Electrons or ions?
Huh?
Ions.
Electrons.
Electrons.
Did I say ions? Yeah. So electrons would be defined by the contact potential of the Schottky contact. And no matter, like how you move the ions, the electron boundary condition would not change. So what you're doing in your system is you say, well, I put both in the ionic system. I also can describe the change in the resistance, which is an electronic phenomenon.
It's not that everything is in the ionic system. What changes through the pulses is that you change the structure. Namely, you move the ions.
Yeah.
Then the ions remain there. That's why it's non-volatile. And then you go to bias, and then the conductance is just given by the electrons. Now, these electrons move in a landscape of varying ionic concentration. So you modulate the resistivity along these conductive paths, and on those conductive paths, you have just normal electronic conduction.
Yeah,
so
what I'm saying is that the interface itself.
Yeah, the interface could be blocking or non-blocking. Here I just show blocking. You could just release that and allow oxygen to go out of the system or get into the system. Those areas will be just relatively small perturbations. The goal of this is just to highlight what is crucial. So this is strict to the bones. So you don't need to really take care of the Poisson equation. It's immaterial. This system is, all the electronic power is completely very well streamed. So the important thing is that with the pulses, you move ions. These ions change the local resistance of the system. And with that, you get the effect. So that's the whole point.
Isn't it that at the interfaces, like the ion concentration and the electron concentration are decoupled? So what you're saying is like it's kind of a local electronegativity assumption that if I change the ion concentration, I also change the electron concentration, right? Because you have to somehow couple the concentration change in the ions with the change in the resistance. So you have to couple the ionic system with the electronic system.
Sure, the more, yeah, but it is not always. Different systems will, a key point there is how do you relate the vacancy concentration to the resistivity. And that is very strong material dependent. For instance, in this case are manganites or Y2CO. These are rather metallic systems. So the main effect of putting vacancies there is just to break the chains, the PD chains that produce the conductance. So having more vacancies increases the resistance. TO2 is completely different. TO2, if you don't have vacancies, the system is very insulating. So the role of vacancies there is to produce carriers. So different systems will have different constituency, if you want, conditions. So this is a simple one adapted for these conducting peroxides. For titanium oxide, I would have to change the things. The more vacancies you put, the lower resistivity you will have. It's opposite to this. So you have to make specific assumptions for each one of the materials. But again, I don't think that those are that important. That the main effect is there, and the key point is that just by changing the oxygen vacancy profile, you change the local resistivity properties of the system, and on these different resistive chains, you get different conductive properties. So that's the whole point. And things can be adapted for each one of the different materials.
No question. Any more questions?
You're exactly right.
Just a little following up the previous question that in the beginning, of course, you motivated the excitement of the problem based on that it shows up in all kinds of oxides. Now, the last 10 years, we spent a lot of time wondering about the strong correlation aspects of all of these oxides. Unless I missed it, you didn't place too much emphasis on Coulomb interaction of charges or Mott physics or anything like that.
Yes, the original motivation for me to get into this was, of course, I'm coming from the strong correlation effects in oxides, and I said, well, here we may have strong correlation effects, so we have strongly correlated electronics. That seemed to be like a very exciting idea. Now, time has shown that probably strong electron correlations is not playing a big role here. Nevertheless, something is playing a big role here, and what I think is that a unique feature of the oxides that their conductive properties are so much dependent on the oxygen concentration on this system. Eventually, protein systems that may give rise to a huge variety of exotic phenomena associated with strong correlation. And the key point is because the conduction is done by narrow bands. These are deep electron bands which are sort of hesitated between localizing and extending. So that's why oxygen has such a big effect. Very, very different from less correlated materials, which may also be oxide. But only in these 3D oxides is that you have such a big effect of tinkering with the oxygen concentration or the oxygen vacancy. So that's why I think it's important. But I still hold the hopes, we've seen in Stuart talk yesterday, that B2O3 may have some strong correlation effect there waiting for us. So I still keep my hopes high, and also with improvement in heterostructure publication, perhaps we'll get a better handle to all this, and we can get the system to switch by strong correlation.
Can I ask a question? So you were showing numbers. So if you look at the thickness dependence of the effect in the two-tone device, when the Schottky region doesn't have the arm ratio is changed, so what are the consequences of the thickness
Of the thickness of the oxide is not much, because everything is happening at the interface.
when you get to a thickness which is comparable?
Yeah, when you get into a thickness comparable to that, I think you get into that thickness is just below, say, 10 nanometers or something like that. That's what I think it's a. So all these Hewlett-Packard experiments, I think they're already working at the level of these interfaces.
In your model, you showed the resistance versus voltage curve. You move the oxygen vacancy around.
Yes, the key point is that you don't need to move them across the system, just in and out of the interface. So that's why the system can switch very fast.
That region is very critical.
Yeah, the region is very critical.
If the region goes down, then the effect is diminished.
if the two regions, if the two regions overlap, I think you're going to get into trouble. Yes. I mean, if the system is symmetric and the two regions overlap, I think you're getting into trouble. You really need to have at least one well-defined interface. That would be, I would guess, more like 10 nanometers. Yes, but having a symmetric system there, it's not so evident. How you build a symmetric system of 10 nanometers.
There's a particular what is the concentration of it?
The concentration is 10 to the minus 4. So we just assume a very small concentration of it. Yes. Well, we try to put numbers that were not completely unrealistic and that we can deal with our numerical means, because, you know.
Any final questions?
No, there seems to be an interesting difference between Stan's model yesterday and yours today. That in Stan's case, his interface is moving. So, if I understand correctly, is that one way of translating or moving between the two models that you could take as a variable the thickness of your electrode layers. On the other hand, what you show that even for a fixed W in Stan's language, you can show many of the switching phenomena.
That's right.
To explore the difference between the two.
That's right. Well, you can get into the equation. Things do move through the interfaces, but the way to think of this W of the Memristors thing is just the total quantity of vacancies that you put into the interface. So this you can take it out. So the proportion of vacancies that you put there. Within the interface, the simplicity of the model will tell you that anywhere you put it in the interface, they contribute the same. And anywhere you put it in the valve, they contribute the same. So the only changes you get it from getting from the interface into the valve or from the valve. So the ratio between the two will be this W that is associated with the position, the physical position in the model of that.
So Stan, would you like to make a comment?
Well, I mean, the issue is that this is, what he's doing is essentially a Mach-Hubbard type calculation. I mean, he's got he knows how to solve the Hubbard type of Hamiltonian, and he's looking at hopping in a very constrained way. I mean, what we
This
did
is not what Hubbard. No,
it's essentially it's similar. I mean,
no, I strongly disagree. There is nothing more Hubbard here. I mean, if I know something, I know more Hubbard physics. I'm an expert on that much more than this. And I know that this is not more Hubbard.
Oh, I'm just.
We can discuss about more Hubbard physics, and I can give you a full talk on that. This has nothing to do.
You've got a system in which you've got a linear string of cells, and you're looking at interactions between neighboring cells.
No, the cells do not interact. It just transfer vacancies from cell to cell.
Well, that's the interaction of the cells.
This is as classical as you can get.
Okay, so look, what we did is we solved the full drift diffusion equations for electrons, holes, and vacancies in the system. All right? And we did that self-consistently with the Poisson equation, essentially used to couple the motion of the electrons and the vacancies. Okay? So the issue is that we were looking at a complete self-consistent calculation, looking at both drift and diffusion of the charge carriers and the vacancies, and we were able to follow in time how the vacancies move, and as the vacancies are moving, we're able to follow in time how the conductivity of the system changes. So, I mean, we essentially have a complete picture of where both the distribution of charges because of the vacancies, and actually also their, which ones were charged and which ones were not because of the profile in the system. And we're able to look at the potential that creates and how the electrons respond to that potential. Okay, and this comment back here was exactly correct, because what happens is the electrons respond to the potential that's formed by how you arrange the vacancies in the system, and that's in turn what determines the conductivity and resistance at that point in time. So, you know, I don't know how to do something like this appropriately, other than to effectively do that complete type of calculation, where you really are looking at the coupled system with the Poisson equation as the coupling agent.
Yeah, but that's fantastic, but what I'm trying to say is that it's probably not worth the effort, depending on what you want to look at. What I'm saying is that this system seems to be very, very well spin, so Poisson equation is not that important, and this system is pretty much, the two components are pretty much independent. On the pulse, really what happens is you have the oxygen migration, and then in the bias regime, all the oxygen stay put, and then you have just pretty Garden barionic conductivity that changes from position to position depending on the concentration of the electron find. It's just simple as that. Now you don't need to do the Poisson for that. If you do that, you may be wasting a lot of effort. So it may be perhaps more precise. But on the other hand, you will not be able to do a very extensive simulation through many loops and try to get all the qualitative features that you can get in order to show why the table with Dex happens, what is the role of the asymmetry, and how is the degradation going on, and what is the long time description of all these. We can do thousands of loops, and I'm pretty sure that if you do a microscopic type of simulation, you will not be able to complete more than perhaps a full loop. So I think there are always things to win and give up when you look at the problem with different degrees of approximation. That's it.
Okay, well, thank you very much for that interesting discussion. We continue. So I'd like to introduce now Professor No from National University, who will talk about unified models and both unipolar and bipolar.
University. First of all, I want to thank the organizer of this conference for inviting me to this interesting and exciting workshop. And today I want to talk about the unified model to explain the both unipolar and bipolar lattice switches. Although I'm talking about the model, I'm the experimentalist. So that means that my model will be very, very simple. But my point is that even with very, very simple model, we can explain the most aspects of the unipolar and bipolar resistance switch. That's the point. So before talking my talk, I want to introduce my collaborator. And this work has been mostly done by my postdocs and students. And also I got a collaboration with Professor Kang from our university. So actually most of the work I present today has been done by Mr. Shin-Bum Lee and Jason Lee. And Jason Lee did all the simulations. And also I got a collaboration in Korean communities, especially from Samsung and KBSI. So this is the outline of my talk. I will first give a brief motivations, and then I will explain the random circuit breaker network model. Then I will try to explain. I will use this random circuit breaker model for the unipolar resistance switching. Then I will try to modify this random circuit breaker model to explain the both the bipolar and unipolar resistance switching. Then if I have some time, I will try to talk about the fractal nature of the population channel in the unipolar resistance switches and so on. Yesterday and today, there's a lot of talks on the resistance switching, so I don't have to give in detail how it works. However, I want to point out quite a few things. The first thing is that the first paper on the resistance switching has been reported in 1962. That's about 40 years ago. So this is a very old problem. So in 1970, there's already a review article by the Relay, and they have a table about the material which shows the resistance switching that is about more than 2 pages long. This is a partial list. So it is already known that this kind of behavior has been observed for many times. In addition, this is the collection of the IV characteristics actually done by Dr. Inoue. And this is actually the material reported after year 200 and 2000. Then if you look at this material, you can clearly see that this resistance switching has been observed in binary oxide, perovskite, sulfide, organic, semiconductors, and so on. So this is a general phenomenon observed in many material systems, not just in oxide. So, and also if you look at the details of the IV characteristic, they look be quite different from sample to sample. So this all indicate that we need to develop a physical model which is not specific to material systems, something like oxide. So what is the general phenomenon of general physics? So let's think about the Earth. On the Earth, we can have a different kind of objects, something like apple, or mobile phone, or scissors, and balls, and so on. They are objects made out of the different material. However, if you put this one at certain height, it will all drop to the ground. So there's a general physics allocated there. So basically, I try to look for the very simple general physics that is located in this, the resistance switching phenomena and so on. And although all the IV characteristics is quite complicated and chaotic, the most of the resistance switching can be classified roughly into these 3 types. The one is called as the bipolar memory resistance switching. In here, we have 2 states, so low resistance state and high resistance state. And this reset process, so changing from the low resistance state to the high resistance state occurs at one polarity. And also the set process is actually occurring at the opposite polarity and so on. On the other hand, at the unipolar resistance switching, these both reset and set process occur at one polarity. So it's basically symmetry about the polarities. But there's a little difference between this memory switching and threshold switching. So there's a 2 state, the low resistance with the high resistance state. For the memory resistance switching, they are stable at 0 bias. So it's non-volatile. On the other hand, if you have a threshold switching, then one of the states is not stable. So there is only one stable state at the 0 bias. So this is a volatile. So we can distinguish this one as a memory, and this is a threshold switching, and so on. So let's move to the random circuit breaker model for the unipolar resistance switching. So in here, we are basically concerned about these 2 objects, this switching phenomena. And this has been observed by many workers already, and many people think that this is maybe coming from the different origin. So our question is that, do this unipolar memory and threshold switching is actually coming from the different origin or not? Or can we describe both resistance switching within one very simple model? That's our question. The reason we raised this question was that we actually observed a very interesting phenomenon. So one of my students made the PT nickel oxide PT capacitors, and in order to change the heat dissipation through the bottom electrode, he changed the thickness of the bottom electrode. So at the very thin bottom electrode, where the heat dissipation is very small, he actually observed the non-memory switching, so threshold switching. On the other hand, if we increase the heat dissipation by increasing the bottom electrode thickness, he observed the memory switching. So yes. And also, he picked it up, this 30 nanometer bottom electrode sample, And originally it shows the threshold switching, but if it cools down, this memory switching recovers. Then warming again, then threshold switching, cools down again to 80 Kelvin, memory, and threshold, and so on. So it's somewhat cyclical. So this indicates that there should exist some kind of a reversibility between the unipolar memory and the threshold resistance switching. This indicates that maybe this memory and threshold switching might be coming from the same origin. And also, another important thing is that in both cases, the thermal effect is very important. In the other words, Joule heating should play a very important role in this kind of the unipolar resistance switching. So we try to make a very simple model which can describe both unipolar memory and threshold switching at the same time. So first thing we have done is that we studied the surface conductance by using the conducting AFM studies. So first, it is in the insulating state. Then, if you increase your voltage, it will make a foam. Then it will be entered to the low resistance state. And when we scan through, we found out that there is a certain spot which has a very low resistance. So there should be a conducting channel below. Then, when we make a reset process, so when we enter to the high resistance state, all this channel disappears. Then go back to the resistance state, and low resistance state again, then this channel appears and disappears and so on. This all indicates that this unipolar memory resistance switching should come from the forming and rupturing and reconnection of these localized conducting filament channels and so on. Then how we can model this kind of a network that is built by these conducting filaments. As you all know, the statistical physicists studied this kind of problem in 1970s and 1980s with a model called as a population model. But unfortunately, the classical population model can describe only the static problem or irreversible process only. For example, let's look at the random resistor network model, which assumes that our material can be represented by in terms of the height and the resistors with the high resistance and the low resistance. So if you have a channel like this, and if you have a population cluster which is made out of this low resistance resistor, then it becomes conducting. On the other hand, if not, then it will be an insulating. So this can describe a lot of static problem in this composite medium type materials. However, this only describes the static model. On the other hand, if you go to the random fused network model, the stories are a little different. In here, they assume that the whole medium will be represented in terms of the fuse, but initially some of the fuse was broken. But if you apply the external voltages, then there will be more current will go through. At certain point, some of the fuse will be broken again because there will be a current distribution. So for some fuse will have the more current will go through, so it will be broken first. Then it will have some kind of the catastrophic effects, so everything will be broken down. So this can explain the irreversible process, dynamic process. However, in the resistor switching, we need a reversibility because we have to change between the high resistance and the low resistance repeatedly. So these two models is not sufficient. That's the reason we propose the random circuit breaker network model. So in here, we assume that all the material can be represented in terms of the random circuit breaker. So as we know, the circuit breaker has a two-state, on-state and off-state. So if you just change some kind of the changing rules, switching rules properly in each circuit breaker, we can probably describe the most aspects what is occurring in the random resistor, the resistance switching. So, and also this model actually is a very reversible process. You can actually change from one to the another. And so that's the reason we actually started working on this new population model. So what is the switching rule? So initially we assumed that the switching can be controlled by external bias. So the reason we did that is that in such a case, it is very simple to simulate the region, because only thing we have to calculate was that we have to calculate the voltage distribution at each capacitor, circuit breaker. Then, by solving these Kirchhoff equations, we can actually calculate the voltage applied to each circuit breaker. Then we can try with it. So it's a very simple model. So there is some kind of voltages where this high resistance circuit breaker will enter to the low resistance break. This is called as anti-fuse, or this is actually very similar to the dynamic breakdown in each component. On the other hand, the V-off cases, the low resistance state will be changed from there to the high resistance state, and this is they call as a fuse, or this is a recovery of the insulating state by the electric field. However, I already showed this data. We have a thermal cycling between the threshold to the memory, which indicate that the dual heating should play a very important role in this kind of unipolar resistance. And also, earlier one of my former students did a very interesting work in fast-state synchrotron radiation lab. So what he has done is that we used the VO2 symptom, and this is actually threshold switching, show the threshold switching. When it becomes metallic, he looked at the surfaces and measured the temperature. And he found out that there is a certain region has a much higher temperature, indicate that there is a dual heating actually opposite this system. So that's the reason we changed one of the switching rule. So this is like this. So in here, if it is in the low resistance state, but if the temperatures go higher than Tc, then it will change into the insulating state. So this is something like annealing, thermal annealing effect. So with this one, we have to do two things. We have to calculate the voltage distribution across the circuit breaker, and also we have to calculate all the temperature of each circuit breaker. That can be done, obviously that's a completely possible. But anyway, so I will try to show the result of our simulation. So we did a simulation with 20 by 50 square lattices, and we initially assumed that some of the circuit breaker is on state. So the red in here is the on state, and green in here is the off state. And we also performed the simulation by fixing some of the defects. So the initial red line is we think that is something like a defect. Sometimes we just fix this defect and assume that it does not change, but the result will be the same. Sometimes we take out certain point and did a simulation, the result is basically the same. So we'll try to show our simulation where this can be changed, but initially this was on and all the rest of the other things is off. So when we start applying our external voltages, there's nothing happening initially. However, when you reach around 8 or 9 volt, you can start to see that you do have a population channel developed across the sample. So if you look at the population channel, then in here, we have it approaches the certain voltages. Then, if at high enough voltages, you can see that some of the circuit breaker in this region will actually satisfy the switching rule. But after it is switched, then around this region, the some more circuit breaker will satisfy the switching rule. So it just propagates. So it is a kind of a self-organized evolution process in here. So that is the forming process. The polyfill reset and set process. So in here, we put the Joule heating effect over here. So as we put through some more current, then the current will go through, the temperature will rise. So this region, the temperature will get higher than the other region because most of the current will go through this hottest one. Then suddenly it will break down. So it will change into the high resistance state. Then if you keep increasing your voltage, then you will experience, this region will experience another direct breakdown. So it will recover. So that one is the reset process, the other one is the set process. So with this simple model, we did a lot of simulations. So first, I try to show you some simulation which has done with and without the Joule heating. They actually give the same result. So I'll try to show those results first. So first, this is the typical IV characteristic curve forming and the reset and set process. Sometimes it shows this multi-step, the multi-level switchings. The simulation can have the same thing, and if you change the initial, the defect configuration a little bit, sometimes you have a multi-step, multi-level resistance switching. And also, this is a current driving switching, which is first done by Samsung before, and you can have the same thing, and you can also simulate this multi-level resistance switching when we use the current driving switches. And also, a lot of people reported that there is a wide distribution of the switching voltages in here. The simulation can give exactly the same thing. And sometimes we observe the very weird behavior, something like this. During the switching process, you can have more current coming up. That can be understood in terms of this model. Also, now I try to show you the effect we need a Joule heating. So if you look at most of these IV curve for the unipolar resistance switching, they are always concave downward. So if you do not include the Joule heating, our prediction shows that it should end up straight line. However, when we include the Joule heating, then as you can see here, that the predicted line is concave downward. Because at the higher temperature, the resistance will go higher in the metal region. And also, this is the experimental data for the thermal cycling. And this one is the simulation data. We can actually show exactly what we have observed. So this all indicates that Joule heating is very important. Also, this indicates that the difference between this stressor switching and memory switching is coming from the stability of the low resistance state. So this is a summary about the unipolar switchings. So now let's move on to the unified models to describe the bipolar and unipolar resistance switches. So now we try to concentrate on these two. So we are asking you that are these two resistance phenomena, switching phenomena, are related to each other or not? So one of the reasons we raised the question was that we actually observed another interesting phenomenon. So for example, we just in one sample, which is the polystrontium titanate. Originally, it showed the bipolar resistance switching. Yes. But if you repeat suddenly, with the exact same condition, it enters the unipolar resistance switch. Then after repeating several times, just go back to the unipolar resistance switching. Then come back to the bipolar and repeating again. So how can this kind of thing can be happen in the system? This is a very complicated experiment, but very rarely observed in this kind of bipolar resistance switching. So the question is that can we describe the occurrence and the interchange between both unipolar and bipolar memory switchings in one sample with one simple model? In order to do that one, we have to understand the importance of the interface that is already emphasized by many workers in here, many speakers here. So I'll just skip this one. And so this is a very nice pictures that is proposed by the Dr. Sawa. So the first thing we have done is that we actually measure the resistance of each system, each state. So initially, when it's in the unipolar resistance state, the high resistance state is insulating, but low resistance state is metallic, as is shown here. So in order to describe this one, we need two things. So one is a metallic, and the other insulating, and the switching between those two, we can describe the changes between this state, which was already demonstrated earlier. On the other hand, if you look at the bipolar resistance state, both of the low resistance state and high resistance state are insulating. This indicates that this insulating state should be interpreted with two new insulating states. So the simulation we have to modify in such a way that in the interfacial region, we probably have a bipolar switching from the pattern formation at the interface, but the unipolar is coming through this pattern formation through the ball. But in here, the unipolar, we just use the two state. By bipolar, as shown in this column, we need at least three states. So simulation is a little more complicated. However, we can do the simulation. So we just have a three state at the interface. And so in here, there's at least 5 switching rules we have to show in detail. But I think the most important switching rules is these two states, between these two insulating states. And we assume that this has polarity dependence. So that the positive polarity is switching one way, and the negative polarity is switching the other way. So with this very simple rule, we perform the simulation again. So we assume that out of this 20 layer, first 3 or 4 layers become in the surface state. And then we perform the simulation. So we increase the power voltages. So initially, with some kind of defect or lighting existing in the system, initially there's nothing happen. But you can see that at certain voltages at the surfaces, it will be entered to the lower resistance state. Then you can see that throughout the bulb, you can have a percolating, very low resistance state. So this all indicate that in the bipolar, the resistance switching, many people are using this forming process, but forming state is required because to create the conducting channel throughout the sample, because that will actually provide the main supply of the current to the system. That's the reason you need a forming process in the bipolar switching. Of course, if you make film thinner and thinner, then you do not need this forming process. That actually has been observed by many workers already. And if this kind of the channel has been formed, then we apply the voltages. So with the negative voltages, so then you can see that some of this low resistance state changes to higher. But if you go back to the opposite polarity, this will be critical domain. So this all indicate that this in the bipolar resistance switching, the set and reset process should occur in this interface region only. Then we can describe the whole thing. Now, let's move on how this bipolar switching can be changed into unipolar switching. That's important because suppose you have this kind of a network, then the percolating network. But suppose some of the state attached to this percolation network in this interfacial region has the very, very highly conducting region like this. Then what will happen will be, because it is have a very high conductivity, maybe the broken down of this, the infiltrator layer that occurs in this region. So it will enter to the unipolar. So what we have done is that this is the experiment I already described to you. So with a particular defect the configuration, we can actually find out a solution which can actually do the same thing like this. So it changes from the bipolar, unipolar to bipolar to unipolar, and so on. So this is the experimental data. This is the simulation data, which can actually mimic exactly what is happening in our Johnson tightness symptom. So our modified RCB network model can describe the reversible changes between the bipolar and unipolar resistance switching quite well. And the occurrence of such kind of reversible changes to resistance switching should be determined by the initial configuration, initial distribution of the defect. So it is very important to control the defect in order to use the RLM devices. And also, many people reported the polarity direction changing. So in here, original simulation has been done in here with this kind of polarity changing. But if you change this polarity direction, then you can actually see that polarity direction becomes reversed. It's just been observed by many workers. So this model has very simple model can describe the many aspects of this bipolar switching as well. So this is a brief summary. And if how many time do I have?
You have about 5 more minutes.
5 more minutes. Okay. So maybe I will try to show some of the how this